In this problem, we're looking to find the tension in each rope to hold this 20 kilogram lamp in static equilibrium. So in our find, we need to find every tension of the 5 ropes that we see here. So I will call it TAC, TBC, TCD, TDE, and TDF. So notice the naming convention I'm using just alphabetical listings here for all of the tensions. That way I don't accidentally confuse myself by having a TAC and a TCA, for example, which would be the same rope, just named differently. So always using alphabetical order is going to make sure that I'm accounting only once for each of the tensions. So there's 5 tensions I'm asked to find here. And we know going into this, we're in 2D particle equilibrium. We're going to be able to get only 2 equations, 2 equilibrium equations out of each free body diagram. This is going to be a case where we actually are going to have multiple free body diagrams necessary to solve our problem. So what are we given? We're given the mass of the lamp. So the mass is 20 kilograms. All right, it's an equilibrium problem. We're certainly going to need free body diagram, but actually we need multiple free body diagrams for this one. So I'm going to start with what I'll call free body diagram 1. No coordinate system is given, so I can establish my own. So in free body diagram 1, even though it's the typical x right, y up, I'm just going to make sure I explicitly put it here. Okay, so I need to choose my particle of interest, or in this case, particles of interest that I want to model. Well, I'm going to need to know the tension in every rope, so I can't do that with just a single particle, but I want to choose particles and have enough information that I'm going to be able to have a couple of free body diagrams and all of the tensions are going to appear. So in this case, it doesn't really matter which I start with, but looking at how this is set up, D and C are connected to the most ropes, and they're going to be able to provide me with the information I'm going to need. Technically, we could also model F, but I'm going to take a little bit of a shortcut here because of knowing how cables are going to be working. So actually, the tension in DF, I'm going to be able to solve right away, or I could technically draw the free body diagram of F, but it'll be unnecessary in this one. I'm going to start by modeling what's happening to point D. So that will be my free body diagram 1. Actually, I'll just call it D since that's the particle that I am going to be drawing. All right, so D is the center of this. So I want to model all of the forces that act on D. So there's 3 ropes connected to it, and also always ropes or cords I'm going to assume are in tension, and they can only act in tension. So that means that all of the ropes are going to have arrows coming out from this center point at D. So I'll work in the upper first quadrant. So I have the tension in DE. I don't know what its value is yet, but I do know its direction because the force in the rope has to be directed along the rope itself that points from D to E. And I was told that it makes a 30-degree angle from what I am calling the positive x-axis. So that's one unknown. I have the rope that goes from C to D or D to C, but I'm calling that CD. And again, I know it's horizontal. It's in what I'm calling the negative x-axis in this picture. And then finally, I am going to have the rope DF directed along its length. Now here I can take a little bit of a shortcut because on the bottom, that rope is connected to the lamp. So I know that the tension in this rope has to equal the weight of this lamp because it's directly connected to it. So really technically I should draw a picture for F to prove that's true, but this is a case where it's going to be pretty trivial. I'm just going to link it together. So I know that the force in this is the weight of this lamp. So here I have to be careful. I was given the mass of the lamp to be 20 kilograms, but I need to include the weight of the lamp. So I need to here multiply my 20 kilograms times gravity of 9.8 meters per second squared in order to get the weight of the lamp in newtons. So to 3 digits of precision, that lamp is going to have a weight of 196 newtons. So from here, I can start writing equations. I can actually also draw another free body diagram, but I'll be able to go back and forth here. The first equation is actually going to come from observing that dF is directly connected to the lamp. So right away, I will know that dF must equal that 196 newtons. Could have a free body diagram. I don't really need it for this one. So that'll be my equation 1. Now, I can now have two equations from this free body diagram. Now, looking at the free body diagram, there's two unknowns. I can get two equations. So I might as well start writing equations because I'll be able to start solving for things now. Or I could draw another free body diagram and write all my equations at once and then solve them all at once. Either method is okay. But I want to do this as I go. Now, looking at the free body diagram, before I choose what direction to draw the forces in first, I can sum the forces along the x and sum the forces along the y. Again, the order doesn't really matter, but looking at this, DE and CD both have x components, but DE has only a y component. So I'll actually start with the y direction in picture D for this sum of forces. So notice here I am indicating which free body diagram this sum of forces is coming from because I'm going to have multiple. If we only have one free body diagram, then it's apparent which one it's coming from. We are in static equilibrium, and the thing we'll have to realize in this problem is that if our system is in static equilibrium, every component of the system is as well. So that means that this point D must be in static equilibrium if the whole system is. And we'll see that as we go to draw free body diagram C next. So in this picture, in the y direction, I'm going to have all of the weight of the lamp down in the negative y direction, none of TCD, and then sum of TDE. So TDE and sine 30 degrees. Right? And I can actually move on. I can go to the solve step and then I can come back. Because if I look at equation 2, there's only one thing in that equation that I don't know. So I can use it to find the tension in DE. Right, so if I solve equation 2, I get 392 newtons. And it's positive, so that indicates it is indeed in tension. And really this has to be because it's a chord. So if we got a negative answer, if it was indicating it was in compression, we did something wrong. So TDE we have solved for, so that's done. And also DF we solved for, so that's done. All right, so now we can actually go back to the equation step and I can write equation 3. Still using this free body diagram, I have not yet summed forces in the x direction, so I can do that now. In the x direction, all of TCD points to the left, so that's going to be negative. And then just the horizontal component of DE, cosine 30, lies in the positive x direction. So again, notice from the solve step, I do already know the numerical value of TDE, but in my equation step, I am not going to write the number. I'm always going to keep it algebraic until that solve step, because I always need to be consistent with how I drew my picture. So in the picture, it's TDE, and this component points to the right. Now in the solve step, looking at equation 3 now, I can use my results from equation 2 in equation 3 because I know DE, so TCD is the only thing I don't know. So I can solve for TCD. And it's equal to 339 newtons. Again, it's positive. It agrees with our assumption of how we drew it. It is in tension. So TCD we have now solved for. So that we have taken care of. So there's still two tensions though that we need to find, AC and BC. They don't appear in the free body diagram though. We've exhausted this free body diagram. We've gotten the two equations we could out of it. So now the only way to get more equilibrium equations is to draw another free body diagram. And that's what I can do. I can now draw the free body diagram at C. And I need to establish a coordinate system for point C. I will use the same one, x right, y up, but again, I need to indicate that that's what I'm doing in the picture. So acting on point C, I have three chords, CD, BC, and AC. CD actually appears in both pictures, and that's what's going to link this together. Again, even though I know its numeric value, I am just drawing it as a variable in this picture, and later I'll use the information I already know in order to solve the rest of it. Right, I have AC acting, also in tension here, and we are told it acts with that 3, 4, 5 triangle. And that's TAC, and then TBC, and that's acting 45 degrees from the horizontal. So I have my complete free body diagram for point C now, the three chords it's attached to, all the directions using a ratio triangle, using an angle here, and now I can proceed to write the equilibrium equations based on C. All right, so looking at C, TAC, TBC are both acting in the x-axis or in the x direction, so that's going to be two unknowns. I do already know TCD technically. And TAC, TBC also both are in the y direction. So starting with x versus y isn't really going to make a difference. So I'll just write x, and this is picture C. So in the x direction, I have pointing to the left 3/5 of TAC. I have minus TBC times the sine or the cosine of 45 degrees, which is going to be square root of 2 over 2. So I can just write that directly here. Or cosine 45, either one is fine. Plus TCD, which again, I already do know is 339, but I'll wait for the solve step there. So I have two new unknowns I've introduced, but I don't have enough equations yet to solve for them. So I'll go to my fifth equation, summing forces in the y direction in picture C. So here I have positive 4/5 TAC, since that is pointing up. And pointing down, I have minus sine 45, which again is root 2 over 2 if I want to be exact, TBC. All right, so looking at equation 4 and 5, like I saw from the picture, they both have both of my remaining unknowns in them. So I am going to have to solve these simultaneously. So using equations 4 and 5, and I can put TCD in there, I can solve these simultaneously, and I'll be able to find TAC and TBC. All right, so I'll throw these into Mathematica. Now you see I already did use Mathematica to solve for TCD and TDE, even though that I could have easily done by hand. But what I need to put in here is my equations. So I did it this way. I said 0 equals my equation 1 equals equation 2 is going to equal, well, actually that's 2 and 3, and I can add 4 and 5. There's different ways I could be setting this up, but I'll do it this quicker way here. So equation 4 I need to put in here, so negative 3/5 TAC minus square root of 2 over 2 times TBC plus TCD. And finally my equation 5, 4/5 TAC minus square root of 2 over 2 times TBC. All right, so I can set this to solve. Notice I'm using the set precision command on the outside. I'm doing that so that it only returns 3 decimals of precision, or 3 digits of precision. I don't want any more than that for this. All right, so pressing go on this is going to solve these 4 equations for the 4 unknowns, TDE, CD, AC, and BC. So again, 2 of them we already knew, the 329, or the 392 and the 339 we already knew. So it turns out TBC, we get a positive 274 for BC. So that means it is indeed in tension. And for AC, 242. And I'll copy down here TDF, since that is also we were asked to find 196, and that would be in tension as well. All right, so here are the 5 tensions in order to keep this system in static equilibrium as it's drawn with that lamp that had a mass of 20 kilograms, which is a weight of 196 newtons. This is what it takes. As a check, all of the values we found were positive, which is a good sign because we assumed tension, and these cords can only hold tension. If we found any one of them was negative, but we assumed it was in tension, then we would have made a mistake somewhere, or it would not be possible to maintain static equilibrium in that case.